We have two talks today. Our first speaker is Nick Gabriel, who is currently a sixth-year PhD student in the physics department at the George Washington University, supervised by Dr. Neil Johnson. Nick is interested in applying graph and operator learning approaches to understand and model complex social systems. Previously, he has interned at Massachusetts General Hospital and Brookhaven National Laboratory. Welcome, Nick. You may want to start the presentation.
Sure. Thank you for the introduction. Yeah, so my name is Nick Gabriel. I'm advised by Neil Johnson, who unfortunately couldn't be here, but we're both in the physics department at GW, and we both study complex systems physics and using methods of statistical physics to understand mostly social systems. But we're interested in any type of complex systems. So yeah, just a quick overview. I'll introduce sort of the problems and opportunities in modeling complex social systems. And then I'll do some background on like hidden geometry and renormalization of complex systems from the physics literature. And then I'll present our multi-scale operator learning framework in order to try to address some of these challenges and also integrate some of the physics literature into deep learning frameworks. And then I'll present two applications. Okay, so there's sort of been a dichotomy historically between data-driven and hypothesis-driven modeling. And so on the data-driven side, we have a lot working for us in terms of scalability, because the number of model parameters k does not scale as the system size, or it doesn't have to. In practice, you may want to scale up the number of parameters as you have more data. But in principle, so this is just like a hidden layer without biases. And we can see basically the number of parameters is just independent of n. And then over on the hypothesis-driven side, if we're looking at coupled models, like I have written down here, something that looks sort of like a Kuramoto model, we actually need n squared parameters for the couplings, which is not going to be scalable to large systems. But we may still want to draw some, we definitely will still draw some inspiration from sort of some of these physics approaches, sort of mean field approaches, clustering approaches. And one thing we really want to get at is explainability of our models. And so that's sort of something we'll focus on as sort of an ad hoc step. Okay, so modeling complex social systems. There's definitely some pretty large limitations that sort of frame the problem. So we don't have exactly known dynamics a priori in basically any situation. So we're essentially always solving an inverse problem. And then in general, systems will be non-ergodic, irreversible, and open systems. And so that's to say the dynamics themselves that we're solving an inverse problem for will not be stationary. But we do have a lot of things that we can take advantage of. So presumably there's some learnable regularities in dynamical data, which we'll kind of see in the examples. And then we have a graph structure, which sort of has a hyperbolic or tree-like structure. And then we may have auxiliary data sources, or I'll say from our point of view, there are auxiliary data sources. Depending on your application, these might actually be the thing you're modeling. But yeah, text, images, those sorts of things, things you would see on kind of social media feeds. And then the system sizes well, depending on your perspective, either small or large, and depending on the data, either small or large, maybe a few hundred to up to like a billion nodes is possible in some circumstances, although for most applications, it's probably closer to 100 to 1,000 nodes. And so basically what we want to do with all this, both these limitations and these sort of data sources, is we want to assimilate graph structure and dynamical data into learnable and scalable dynamics. And so I'll kind of go into the background of the specifics of the graph structure, basically, of complex systems, because they generally have this kind of tree-like structure. They can be modeled well by a hyperbolic hidden metric space, which captures a lot of properties, basically, that are universal to complex systems. So they generally have power law degree distributions, clustering, small worlds, and a tree-like structure. And so studying complex networks in this way kind of goes back quite a while in the physics literature, relatively speaking. So one of the first maybe seminal papers on this was from 2010. And sort of there's been continued progress, I think, in this field, applying it to, or in this line of research, applying it to various structures. They could be social structures, or the brain is another one that's widely studied from this point of view. And so I'll just give an example of why this hyperbolic hidden metric space. So I just found this example yesterday. It's a recent paper. They did matrix factorization of a drug target interaction graph. So they're trying to reconstruct an adjacency matrix from some embeddings Zi and Zj based on a distance metric defined by a particular manifold M. And so, yeah, I basically just quoted their conclusion here. Hyperbolic embeddings required an order of magnitude smaller dimension than Euclidean embeddings. And so this sort of thing carries over to deep learning quite well. Hyperbolic graph networks have been kind of an exciting thing. And so I'll get to that a little bit later, but I'll continue on with kind of the physics background. So I was sort of inspired by this idea of geometric renormalization of complex networks, which is a fairly recent development. But basically the idea was to infer some coordinates and some parameters in order to reconstruct an adjacency matrix. And again, this is based on some underlying metric space. So here they assumed it was hyperbolic. And the example I have shown is the embedding of the connectome. And its renormalization in 4 successive steps here. And yeah, so essentially by learning these, inferring these coordinates, and then grouping together nodes over angular segments, delta theta, that's sort of a hyperparameter, they were able to retain some of the graph properties at each level, essentially in the renormalization, which is quite difficult to do, particularly because of the small world property. It sort of has given difficulties to developing renormalization procedures for complex networks. So this was sort of an interesting success, and I sort of wondered if we could translate this into like a learnable framework. And so fortunately, there were some tools developed in the last few years. One is hyperbolic graph networks, and then the other is basically the series of steps I have written down it's called differentiable pooling. It's out of the computer science literature, so I'm sort of the way I've framed it, we're using it for different purposes, but mathematically the procedure is identical. So assuming we start out with some data X and an adjacency matrix A, we iterate through this procedure where we compute this soft assignment matrix S, which we use to downsample the adjacency matrix or learn a smaller adjacency matrix at each successive level. And then basically we recompute the initial features at the next level as a linear combination determined by the soft assignment matrix. And so an example of what this mapping will do is it'll take us from our initial batch size B. So the adjacency matrix would be, in this case, B times B. And then it will downsample to a 64 by 64 adjacency matrix, and then 16 by 16 and a 4 by 4. And so the choice of the actual sizes in the downsampling are sort of a hyperparameter. You sort of can just leave them large enough and then encourage sparsity by trying to minimize the entropy of the soft assignment matrix. And so assuming this regularization from the entropy is strong enough, some of the, for example, 64 possible assignments will be empty. And then you'll only fill the ones that are basically optimal for whatever problem you're trying to solve. So that sort of sets up most of our sort of framework for sort of learning dynamics of complex systems utilizing graph structure. And so this is broken down into sort of a 3-step framework. So the first thing to do is to encode our initial graph and initial time series data. And I put this third point just to emphasize that we can always include auxiliary data by just appending embeddings to our time series data. So we'll produce some initial embeddings from a first graph network, which is going to greatly reduce sort of the system size and kind of distill information from depending on how many layers you have in a graph network. You're aggregating information from your first hop neighbors for each node in the graph, and then second hop neighbors if you have 2 layers, and so on. And so the second step is going to be, once we have these embeddings, to renormalize them, sort of with that procedure that I outlined in the last slide. And then once we have that set up, sort of this multi-scale graph structure, then we actually want to learn the dynamics. And of course, this isn't actually happening all sequentially. This is kind of a deep learning. So gradients are being passed back through this entire computational graph. But ultimately, we went with sort of a pin framework, and I'll maybe go through a little bit of like some of the choices in the next slide. But our loss function has several components. The first one is just kind of standard data loss. The second is the PDE loss, where F sub I is capital F sub I is just the residual. And then we have a GPIN loss as well, sort of because this problem is ill-posed in some ways. So having additional constraints is kind of a nice thing to have. And then we have the entropy loss from a couple of slides ago. So to give you an example of what this actually looks like, we have some solutions that are color-coded by which node in the next layer they're being, or yeah, in the next layer they're being assigned to. And so the actual time series get added together additively. They're just a linear combination based on the soft assignment matrix, but the embeddings, and this is pretty important, are actually being recomputed through a separate graph network, because they're sort of not going to be a simple linear combination, sort of like the time series will be. And then, yeah, so on top of these figures, we have the initial adjacency matrix and then the downsampled adjacency matrix at the first layer. Yeah, and so what's sort of interesting about setting things up in this way is you have sort of bidirectional information flow from the multi-scale structure to the physics and vice versa. You could also view it as they're constraining one another in order to have consistency sort of across scales. And so we'll look at a couple of applications. The first is going to be the Burger's equation with, actually, sorry. Yeah, so the philosophy sort of for picking applications is since we don't know exact dynamics in advance, we just want to choose models that are quite universal and can kind of capture the sort of dynamics we expect. And then we want to generalize them based on sort of some of the expected features of social dynamics. And so for a Burger's equation, what that would look like is we would just start with an initial Burger's equation. I know this f sub I coefficient is not standard in the Burger's equation, but so usually it would just be 1. But for social systems, we're sort of going to promote these coefficients into operators that are a function of both time and the graph structure. And so the universality of the Burger's equation has been pointed out since at least 1989. So I just have the quote here about how it describes various phenomena, growth of interfaces, driven diffusion, and the large time limit. And they attribute this sort of universality to the fact that it's the simplest generalization of the diffusion equation that contains relevant nonlinearities. And so we actually in our group, we had a PRL recently that was sort of looking at Burger's equations to model social systems on social media. And so this is sort of just my take on that, but I suggest you should read that paper as well. Okay, yeah. So just some results basically for this example. So we looked at a system of almost 3,000 nodes. And this is not the actual graph that was used, but this is sort of just a visual aid. And yeah, so basically, given the setup, it seemed like a logical thing to do was just to do an ablation study. And so this is a one-step forecast. So this is based on some history of the system being incorporated into each one step ahead prediction. And so for the ablation, we did in the graph networks, we did hyperbolic layers and then just standard Euclidean layers. And then still with the Burger's equation. And what was interesting was that seemed to have quite a large effect. Part of this might have been because we kept the layers the same size in the hyperbolic and the Euclidean examples. But it's like almost an order of magnitude difference in terms of the actual accuracy of the predictions.
Hey, Nick,
Yeah.
can I please ask a question? This is Adar from
Yeah.
Brown.
Yeah, sure.
So maybe I've missed something. So what is actually what quantity are you actually embedding here? Because the time series is, it looks like it's uniformly distributed, right? The T days.
Oh, oh yeah. Sorry. So yes, I guess there's basically fixed sensors. For the purposes of plotting, I just picked at fixed intervals some data points and the solutions. But for the actual for what's actually being used in the predictions, I used, I think, a 64 a sequence of 64 time steps prior to the prediction, and then I'm predicting one step in advance.
Got it. And those
That
64
answer?
are like on the like they are not evenly distributed. They are taken as measurements from different time steps, and it's highly.
So in principle, they don't need to be evenly distributed.
Yeah.
Just for convenience, I did sample them at regular intervals, though.
Oh, I see.
Yeah.
So what's the advantage of like taking like embedding this?
What's the advantage of embedding it?
That like, or maybe like are you embedding the quantity of time? What is the quantity that you're creating an embedding of?
So what's being embedded is the history from both a node itself and all of its neighbors. It's one hop.
So the time is just appended to that data.
Yeah.
Okay.
Yeah.
Got it.
Yeah. So yeah, maybe I should actually clarify. So the first two parts of this framework, there's no explicit embedding of the time. The time doesn't get added until we start basically doing the surrogate modeling. So yeah, we at this point we just depend in time, and actually the spatial coordinates are also just dependent as well. And yeah.
Got it. Okay. Yeah.
And then as far as what we actually do with the time, you could do like a Fourier feature encoding, or you could just rescale. You can just try whatever and see what works.
I understand. Thank you.
Yeah. Yeah. So back to the ablation. Using hyperbolic layers seemed to have quite a big difference on actual prediction accuracy of the surrogate model versus the one-step data. And then if we completely remove the PD, we still make fairly accurate predictions, but essentially the model wasn't able to converge very well. It was sort of bouncing back and forth, even like quite late in the training. And so the best result it got to wasn't quite as good as with the PDE. I mean, this is still quite a large difference with and without the PDE. It's like 20%, I think. I think the difference would probably be larger if we incorporated some sort of tricks that would capitalize on using the structure, or sorry, the information from the PD, maybe like causal training, or adaptive sampling, something like that. So that'll be something to look forward to in the future. So one
Yeah.
interesting sort of
Nick, sorry. Can I interrupt?
sure.
Yeah, could you go back to your previous slide? I have a question regarding
Yeah.
the table. So here, you see that on the second row of the table, because there's no PD loss or GPD loss, so in your loss function. So here
Yeah.
this term is relatively large, right? This is perfectly reasonable because you don't penalize violation of the PD. But I'm
Yeah.
curious is this decreasing the loss of data decreases. Is it because you use hyperbolic distance, or it is because there's only data loss term in your loss function this time? So have you
Uh,
ever investigated this?
um, I'm not quite sure I
Yeah,
understood your
yeah,
question.
because in the second row you don't have PDE and GPD terms in your loss function, right?
Uh, yeah.
So I'm curious, is it this low loss value, is it because you only focus on minimizing the data loss, or is it because the hyperbolic distance stuff that is working?
Um, so I would say it might be informative to say how exactly I set up the training uh, with both hyperbolic layers and the PDE. So I set the weight uh, of the data loss to be the highest, and so that was the thing that was sort of focused on. And then in that sense, the PDE loss and the entropy loss were sort of like side tasks. Um, and so the sort of reason for that is if a model isn't making better predictions on the data, there's not really good evidence that it was a good model choice. And so I sort of decided to focus on that. So I don't think I think the having the weight of the PDE loss be non-zero wasn't a hindrance, and ultimately it ended up being there ended up being transfer learning basically to the data loss.
Okay, okay,
Yeah,
yeah, thank you.
at least that was my interpretation of this result.
Sure. Yeah, sure, thanks.
And so I didn't turn I turned the weight of the PDE loss to like 10 to the negative 20, so it's not
Oh,
exactly zero, because I still wanted to see basically what would happen if it weren't. Yeah, I still wanted to know like what the PDE loss was when that contribution wasn't getting any weight. And so yeah, it's like 6 orders of magnitude larger. So I sorry, I'm going to have a visual aid, but it's basically because the predictions will sort of be very noisy. They won't be these kind of smooth solutions that we would expect.
yeah, yeah.
Okay. I think the presentations. Oh, there we go. So an interesting kind of side effect of studying the Burgers equation, and we're doing it in multiple dimensions. The number of dimensions being a hyperparameter basically of the model, is that we can kind of measure the turbulent phase as a function of time. And so here are just some examples of how one could measure that. You could look at vorticity as a function of time, the Reynolds number as a function of time. Sorry, this should be a lowercase f in the Reynolds number numerator. Or you could look at entropy. I'm by no means an expert on turbulence. If you know a lot about that, you might be wondering what exactly I mean by all this. And it's basically just to say that this is something we can look into and see like how actually the degree to which we're in a turbulent phase corresponds to say, various phenomena, maybe like socially, like if we were looking at social media data comparing the vorticity to like political events or something like that, would be sort of something interesting from like a computational social science standpoint. And then since we have this multi-scale graph structure as well, we can investigate cascading or energy transfer between scales. And that just seems sort of like something natural to do. So I figured I would just mention that. So the next application I wanted to look at, this is the Kuramoto model is sort of widely used. It seems like it's mostly used in like neural dynamics as a model of synchronization. But it can also be used for like opinion dynamics if you're looking at social systems. And it's kind of just a generic model for any system that you expect to have synchronization. Yeah, so it seemed like it was a universal model, and so it was interesting from that standpoint. And so in order to generalize it for social systems, we might actually want to make these angular frequencies dynamic and the weights actually dynamic, because sort of in social systems, you don't expect interactions to be constant throughout time. You expect them to also be dynamic. Yeah, so at this point, I haven't actually applied our framework, but I've basically just simulated the forward problem, and you can sort of actually already see some interesting structure in some ways. And so the first thing is, I will just say the parameter that I chose was below the critical parameter value, and so we don't get global phase locking. So this thing R of t is called the order parameter, and so basically it tells you the degree to which synchronization is locked across the whole system. So if you're above the critical parameter value k, this value will actually go up to 1 and then, or close to 1, and then stay there. So since we're below the value, we see there's several collapses and sort of this oscillating back and forth. Yeah, and then looking back at the actual solutions, I know it's kind of hard to make out, and this is a little bit of a mess, but you can actually see there's phase locking of like some particular clusters. Like for example, there's several nodes that are sort of moving together close to the theta equals 0. And so yeah, we can look at synchronization sort of globally using the order parameter, but we can also look at the spectrum of these like individual communities that are like sort of color coded in this graph. And so it's a little bit hard to see. This isn't the cleanest spectrum, but I've plotted 3 different clusters, one of size 163 nodes, one of 23 nodes, and one of 234 nodes. And you can kind of see that they develop independent spectrums. They have peaks in different at different wave numbers. And the sort of decay behavior is slightly different. For 2 of them, it actually looks quite similar, and then for one of them, it seems to decay quite a bit faster. It's hard to say too much given how noisy the spectrum is, but it does seem like, and I would say basically, if we look closer, we're going to see evidence for local phase locking below the critical threshold, which basically if you're thinking about exact solutions for the Kuramoto model, I think people have mostly found those in the thermodynamic limit as n goes to infinity, which is sort of not necessarily applicable to real world systems. So actually being able to approach this with our framework is sort of interesting when we're below the thermodynamic limit, and then also below the critical value of the coupling constant. Yeah, and so sort of based on that example, I was just sort of thinking maybe this measures of entropy can actually tell us about proximity to criticality. And so here's just an example of this is the adjacency matrix down on the bottom at several snapshots. So it's basically at like, and this is for the Burger's equation example that I showed before. And so to start out with, the adjacency matrix is fairly unresolved, and there's a lot of weak connections between a lot of nodes, or they haven't really resolved into communities. And so the entropy is quite high to begin with. And then as we move forward through time and things get sort of resolved into specific clusters, we see the entropy going down and down. And so, yeah, so one thing I'm sort of interested in looking at is how this entropy behaves as we approach a critical point, or as we get, say, global phase synchronization in the Kuramoto model. And yeah, this is my last slide. So thank you.
Yeah. Thank you, Nick, for the presentation. Do we have a question for Nick from the audience?
I have a quick question. Hi, Nick. This is Panos Tinis from Pacific Northwest National Lab. When you say criticality, is this a function, a phenomenon that happens in time or as you coarse grain?
I would say criticality, I'm referring to this as across the network. So when people refer to like criticality in the brain, say, for example, they're talking about connection between distant parts of the brain, for example, when you're close to a critical state.
Right.
And a state in which you'd achieve sort of optimal communication.
Right. But I mean, for this here, the entropy is a function of time, right? T is time.
Mm-hmm.
So does the entropy go towards zero as time progresses, or something else happens and you have fixed the time?
So it would depend on the system and sort of the dynamics of the system.
Mm-hmm.
So in this particular example, it seemed like basically all the communities were resolved, and by the end, there was no ambiguity into which who was neighbors and who was not, and so the entropy began to go to zero. I think in like the neural dynamics literature, there's sort of discussions of being closer to criticality in different states and further away in different states. And so I think that would be sort of a more interesting example to look at. But yeah, my point was just kind of that we can use this framework as a probe in order to kind of quantify criticality in a different way.
Right. But are these four figures here at the same time, or does time progress from left to right?
Sorry. Yeah, time is progressing from left to right. So this is basically, I guess, showing the sort of life cycle of the system. So yeah, so this first matrix is close to the beginning of the simulation. and then this last matrix is close to the end. So yeah, these are progressing in time.
And do you actually renormalize as you move forward in time, or is it just the same?
Yes. So there's renormalization throughout there's an adjacency matrix as a function of time, and there's a soft assignment matrix as a function of time.
Okay.
Implicitly as a function of time. As I said, time doesn't get embedded until actually later on, but that time embedding is going to have an influence basically on this structure, because the gradients are still going to be able to flow backwards to them. Sorry, did that answer your question?
I'm not entirely sure that, what happens if you just push forward in time without renormalization? What happens then to the entropy? It just remains constant? Because the adjacent matrix doesn't change? Or does the adjacent matrix change in time, this Aij of T? I'm not sure if the adjacency matrix changes because of time evolution or because of the renormalization that you do. That's what confuses me.
It's because of the renormalization.
Okay, so time and renormalization happen somehow simultaneously, right?
Yeah. Yeah, maybe I can go. Yeah, so the adjacency matrix is an implicit function of time. I just wrote it as, it's sorry, it looks like an explicit function of time here.
Right.
But it's not. I just did that for sort of to convey that it was actually a dynamic quantity and that we could look at it dynamically. Okay.
All right.
Okay.
Yep. Okay. I'll read more. Yes. How about thank you.
Yes. No worries. Yeah. Sorry. There might have just been maybe not enough explanation of how time was being treated in the framework.
Time is but it is still treated like we understand it, right? You have a network and it evolves. There are dynamics happening between the constituents of the network, right? And it evolves. Is that, or is time something else? Is the fictitious time?
The way time is introduced is the way we actually sample data is we're looking at sort of a look back window.
Yes.
From whatever the current time is to some horizon back in the past, and that's dictating what are the embeddings, what is the assignment matrix, what is the adjacency matrix as a function of time.
Okay.
Yeah. So time is implicit in the first two parts of this framework, and then it only becomes explicit when we actually need to take the time derivative in order to define the PDE. Okay.
All right. I should look at the PRL paper more also to understand how you end up deriving the Berger's equation.
So the PRL will cover that. I would say the specific form of the equation is going to be sort of different than the one you see here, because this one we're learning basically just from the data.
Right.
So it was sort of adjusted to make it more amenable to that.
Yeah.
But yeah, read the PRL.
Okay. Thank you.
Are there any other questions? No? All right, thank you, Nick. We're moving to our second talk. You're welcome to stay. And yeah, like I was mentioning, this recording will be uploaded to our YouTube channel, so you may want to check it out later this week.
All right, thank you.
Yeah. All right. Our second speaker is Zhongyi Jiang, who is currently a senior student at the University of Delaware, majoring in applied math and computer science. He has been doing research in scientific machine learning under the supervision of Professor Lulu since last May. He's also one of the main contributors to the DSD library. Welcome, Zhongyi. Okay? We see your screen. You can.
Yeah. Thanks for the introduction. Can you hear me?
Yes.
Oh, yeah. Today I will talk about is Fourier MIONet, which means Fourier-enhanced multiple input neural network, neural operators for multiple phase modeling of geological carbon sequestration, which is a joint work with researchers from ExxonMobil. In this study, we consider the problem of multiphase flow in porous media. Specifically, we consider application of underground carbon storage, which involved injecting carbon dioxide into the underground geological formation and store in the formation permanently. And there are two components we care about: carbon dioxide and saline water, which components satisfy the mass conservation equation, and here also show several formula to describe the physical background. And I'm not an expert of geophysics, so for more detailed information, you can check in our manuscript. Here we show an example of inputs and outputs. All the inputs and output fields in dataset are saved in a resolution of 96 times 200. The output are saved in 24 times snapshots from 1 day to 30 years. First column A and B is the input, including field input and scalar input. Second column C is the gas saturation output at 6 out of 24 times snapshots. And third column is pressure buildup. Our data set is obtained from Wengege in Stanford University. Very recently, UFNO proposed by Gege has achieved the state-of-art performance in geological formation for carbon sequestration problem. As an extension of FNO, UFNO just use additional UNet in FNO, which called U-Fourier layer. However, there are still some challenges remain. The computational cost is too high, since UFNO treat all inputs as field input, and it asks input shape same as the output shape. So it's need a large training data set. Moreover, UFNO requires a couple of days for training in one GPU, about 16 gigabyte GPU memory and more than 100 gigabyte CPU memory. And here is the framework of multiple input deep neural operators. I think some of you may familiar with it. MIONet overcomes the challenge of computational cost and data efficiency, but the vanilla version of MIONet cannot easily provide highly accurate predictions. Therefore, motivated by previous operator learning model, here we develop a new version of MIONet called Fourier MIONet by leveraging MIONet and UFNO. As mentioned before, we split inputs into two parts: field inputs and scalar inputs. So in our architecture, there are two bench nets to encode field input and scalar input. And the chunk input is only time. And there are two merge operations are used. One is to merge two branch outputs named branch merge operation. And another one is to merge the branch and chunk net outputs named branch chunk merge operation. Next, we use UFMO as a decoder to map from the hidden vector to the output. We need to know that we use 2D FFT and 2D UNet in UFMO rather than 3 FFT and 3D UNet used in the original UFMO. And UFMO directly output gas saturation and pressure buildup at all 24 time snapshots during training and testing. The output side is 96 times 200 times 24. And in our model, during training, we choose different case, and the number of case is donated by bench case. And in addition to bench case, we also choose different number of time snapshots for the chunk net input. And we donate this as bench size and bench time. Therefore, we can train our Fourier MIONet model in two bench size. One is bench case, another is bench time. The output side is 24 times 200 times bench time. So in this way, Fourier MIONet overcomes the challenges of previous methods and combine the advantages of MIONet and UFMO together for learning physical system accurately and efficiently. We compare Fourier MIONet and UFMO.
Excuse me, can I ask a question?
Yeah, sure.
Previous slide, what is the dimension of Q and the last one? Yeah. At the end of the network, here is a Q after the U for yes.
The output shape is like 96 times 200 times bench time, since we have added additional bench time here.
So that's a linear layer or non-linear? The last Q.
And you can see we use like Fourier layer and U Fourier layer.
Yeah.
And after that, we need to like map the vector from hidden space to the original space. So we also have like two linear layer in the last, following by
not the C part. At the main one, there is a Q at the before the output.
Yeah,
Zhongyi, I think come on mean
Yes,
this
yes,
Q,
the last one.
the dimensionality of Q, not the Fourier layer.
And Q is two linear layer. Yeah.
Without any activation function.
Yeah, like in our manuscript, we have like detailed structure of our network.
Okay.
Thank
you.
Yeah, thank you. And here we compare Fourier MIONet and UFMO in prediction of gas saturation. The accuracy between Fourier MIONet and UFMO is almost the same, and Fourier MIONet require much less computational resources. compare with UFO with UFO with 33 million parameters, Fourier MIONet only have 10% parameters, like about 3 million. During training, UFO require 103 gigabytes CPU memory and 15.9 gigabytes GPU memory. But Fourier MIONet only needs 15 gigabytes CPU memory and 12.8 gigabytes GPU memory. And the total training time for Fourier MIONet is 12.3 hours, which is less than 30% of UFO. In additional to the training cost, we also summarize the computational cost during testing. Compared with UFO, Fourier MIONet needs much less CPU memory and GPU memory during the testing. For each case, Fourier MIONet requires 0.041 second, while UFO requires 0.075 seconds. So Fourier MIONet is about 1.8 times faster. And here are 4 prediction examples of Fourier MIONet. Here we also test the generalizability of Fourier MIONet at unseen training time. As mentioned before, we have 24 time snapshots in total. Here we choose to test 3 cases with different amount of training dataset. 15%, 33%, and 25%. In the first case, we use 50% of time snapshots. Fourier MIONet has good performance at both seen time index and unseen time index. And you can see there is nearly no accuracy loss for unseen time. However, UFO only performs well at same time index. This same phenomenon can also be observed for another 2 cases. We know that the behavior of UFO is classical for deep learning model because it is usually difficult to generalize to unseen time if we use like extremely sparse times snapshots. Here, Fourier MIONet can generalize well because we use time as the input or chunk net, which guarantees that the prediction of gas saturation is continuous with respect to time. That's to say, Fourier MIONet obey the physical law, and the gas saturation is continuous over time. So in comparison, UFO use different channels to predict gas saturation at different time. In this way, UFO does not guarantee the continuity of solution over time. To further improve the accuracy when using 25 training data, only 6 time snapshots, you can see that there is a performance drop. We want to train the network using non-uniform time snapshots. We designed 6 different non-uniform sampling cases since the dynamic of gas saturation change fast at the beginning. More data needs to be chosen at the very first time snapshot. For example, if we choose the second time snapshots at 7 days in figure 8, the accuracy at the time 2 drops significantly. For the later time, we need to choose time snapshots relatively ununiformly. As shown in figure D, there are 5 unseen time snapshots between the last 2 points, which makes the prediction of unseen time with much lower accuracy. However, by choosing dense time snapshots at the beginning and relatively uniform snapshots between later times, as shown in figure B, C, E, and F, Fourier MIONet can achieve good prediction accuracy at both seen time index and unseen time index. And here is for example of pressure buildup prediction. And we also give a discussion about 2 baseline network architecture, MIONet and MIONet FNM. Vanilla MIONet use dot product to construct the output. And here, MIONet FNN just replaced dot product by a fully connected neural network. And our Fourier MIONet employing Fourier and U Fourier layers as a decoder. The accuracy comparison is shown in the table below. The testing R-square of vanilla MIONet is the worst among these 3 models. And Fourier MIONet gets the best accuracy. We also show one example of gas saturation prediction between these 2 models. Like another one is UFNO. As we can see, like the Fourier MIONet also generates accurate prediction. However, vanilla MIONet and MIONet FNN result in blurred output of interface structure. And the reason why Fourier MIONet achieved the best accuracy is it's employing Fourier and U Fourier layers. And UFO also use that. So you can see in the right hand side, they perform quite well. And Fourier layers with truncated module can effectively capture low frequency components in the data. Also, UNet in the U Fourier layer is capable to capture both local and global features. And here's a short summary. In our paper, we developed a deep neural operator called Fourier MIONet. And it combines advantages of data and computational efficiency from MIONet and good accuracy from UFNO. Fourier MIONet can also provide much more accurate predictions at unseen time snapshots with only 6 time snapshots in each case for chain. The good generalizability is due to Fourier MIONet obeys the physical law. Here we also give a brief introduction of the time-dependent 3D problem. That is, as we don't know the 4D dataset, we generate a fake dataset with here we choose Fourier MIONet. And so we choose the Fourier layer with 3D FFT and 3D UNet. And the advantages of like Fourier MIONet architecture show more potential possibility for the problems. And that's all for my PowerPoint.
Thank you, Zhongyi, for your presentation, and thank you for agreeing to join earlier in such short notice. Yeah. Do we have any questions for our speaker regarding the new operator? Zhongyi, what is the, so I think you mentioned your earlier slide, you mentioned the output of your operator. So you mentioned that you have two outputs, you have two inputs, right? Two outputs. Could you go back to your slides? I think one output is function-wise. Yeah, here, yeah. So you also have scalar inputs. So you have two outputs, the gas saturation and the pressure, right?
Yeah.
Okay, so it's basically a multi-input, multi-output operator.
No, the output is single. So we use different model to predict these two output.
Also, two independent operators?
Yeah, the input is multiple, like field input and scalar input, and the output is single for gas saturation and pressure buildup. So we need to use two Fourier MIONet model to predict these two features.
All right, yeah, cool. Okay, thank you. Do I have questions for our speaker? Yeah, go ahead, Mer.
Yeah, thank you, Zonrin, and thank you, Zhongyi, for the presentation. I have a few questions. So you have mentioned several times, first of all, there is a manuscript about this. Could you point us to that after the talk or some time later in the chat, if you could? So is this a preprint uploaded already?
Yeah, it has been uploaded in archive. Yeah.
Awesome. Yeah, if you could point.
I'll put it in the chat. I found it.
Thank you. The other question I had was, you showed there was a table in which you compared UFNO with your version of MIONet, right? If you could go to that slide, please.
Yeah.
Right here. So did you try comparing this with just a vanilla FNO? Because I remember you were mentioning about a paper in which they used UFNO, right? Did you try that exercise just with FNO?
UFNO is proposed by Gerger. In their paper, they compare UFNO and FNO, and UFNO performs better. So we choose to compare their best results.
I see. I get your point. My other question is, I'm just wondering if you could explain to us how you get less parameters in your version of MIONet versus the UFNO, just through the architecture that you showed.
Yeah. So here is the architecture of UFNO. In their architecture, they need the input shape is same to the output shape, and the since there are 24 time snapshots, right? So they need to predict output 24 time snapshots in each training step. So, and in our model, because we split the input into two parts. First is like field input, and second is a scalar input, and we also use TrunkNet to encode the time. So we don't know, we don't need to predict 24 time snapshots in the same time. So we add time bench time as additional time bench case. Therefore, we can use 2D version of Fourier layer and U Fourier layer. But the original UFO, they use 3D. That's the reason why the parameter is much less.
I see. Thank you. And just one final question. So when you were showing on the last slide, your 4D problem, right? So then you have to use 3D FNO in that case.
Yeah, that's true.
Okay. All right. Thank you, Zhongyi.
Since we don't have this 3D data when we write the paper, but right now we have the data. So we work in another project in 4D problem. But here, since we don't have the data at that time, so we generate a fake data set in 4D problem. Yeah.
And the data that you used here on this problem is an open source data, right?
Yeah,
the
open
one
source.
Yeah, but the one that you're talking about is probably not open source, the 4D one, or is it?
Since we use a fake data, the number is not matter.
I mean, you're saying there is a new project that you have with 4D data. Is that also open source data?
Yeah. We also that data set is also provided by Google. They have another new paper in 4D problem. So the
Okay.
data set is also open source.
Awesome. Thank you so much. Yeah.
Hi, Zhongyi. I have a quick question. Could you go back to the architecture of Fourier MIONet?
Yeah.
For the branch merge operation, do you add them, or is that product, element-wise product?
Yeah. I would say here the first operation is like just is summation, like point-wise summation, and the second branch chunk merge operation is point-wise multiplication. Yeah.
Okay. So for the branch merge operation, is this better than element-wise product?
If it is possible,
I mean the performance.
Yeah.
New observations from the
I think we have like doing a lot of experiment in that, trying like different operation, and we choose the one with best accuracy. Yeah.
Okay, I see. Thank you.
Are there any other questions? No? All right. Thank you, Zhongyi, for your presentation. And yeah, we come to an end to this week's Quantum Seminar. Everyone has a good weekend ahead, and see you next week. Bye.